Hi everyone, how's it going? This is Siri and I'm back with another PyTorch video. And in this video, we're going to be continuing our discussion on the learning process, the whole machine learning process, the whole training process, and what we do with our data. And in this video, we're going to be actually diving into the first step that we talked about, which was gathering our data. And we're not going to go into the visualization part, but we might, search up an image of a best fit line and, explain the different components that are going on there. So here in this video, we're actually going to be starting slow. We're going to be starting simple. And in the next series of videos, we're not actually going to be jumping right in to, the deep learning part, the neural networks part, right? We don't need that complicated non-linear component added to it right away. I mean, sure, we could talk about, what different non-linear layers are and how that affects the hidden layers and whatever, right? We could just jump into that and talk about it. There's no problem, but we wouldn't get that intuitive understanding that we might get otherwise if we just take it step by step and start off with a simple example. So we're going to get rid of the nonlinear part completely. We're not going to be talking about that. We're just going to be talking about a linear model. Okay? Here, Kepler, what did Kepler use? He used an elliptical model. Okay? And in real life, data is not that, simple. It's not like, oh, all my data points are just going to form a circle or an ellipse or a line. It doesn't work like that. It's so complicated. There are multiple dimensions. It's not just the X and Y. And there's a lot of different things going on. And, before we jump right into it, let's get a completely accurate understanding and a more intuitive understanding of what's going on, okay? And we can do that with a linear model, okay? And, I have a few things here, and we're actually going to be doing the, a temperature conversion, okay? And, so we first import torch, right? And we have some and the example that we're going to be focusing on today is a temperature conversion sort of problem. Okay? And so we have a thermometer, okay? And we're measuring the temperature over the course of time. And, maybe every hour or every 30 minutes or I don't know. Okay? And the only problem that we have right now is that our readings are in an unknown unit. Okay? And we don't know what units we are recording our temperature in. Okay? So we might as well just put the input first and then the output. Okay, and we do have some additional information though. And the additional information that we have is that although we don't know what temperature that we're reading on our thermometer, we do know that when we convert it to Celsius, these are the values that we get. Okay, so this is an unknown unit, and this is temperature in Celsius. Okay, so we have a thermometer that obviously takes the temperature, and there's definitely noise in the data, right? So when we look at the thermometer, we're not looking at perfect measurements. Okay, it's going to be off by a little bit. And it doesn't need to be super precise, right? I mean, it's accurate, but, it's not, that accurate. So there's one source of noise. another source of noise is, when you, first of all, the thermometer might be wrong, and second of all, the accuracy might not be right. And when we convert it to Celsius, it's going to be even further off. Okay, so yeah, and we are assuming, okay? We don't know, but we need to start off with, an assumption about the relationship, okay? In regular deep learning models, we're not going to do this, right? We don't want to have a bias going into analyzing our data. But we can for this sort of situation because we only want to deal with linear models, okay? And this is basically what Kepler did. He thought it would be an ellipse. He stuck with it, and he did his training on that. Okay, and we'll talk more about what the actual training process is, and we'll go over that in this video. We're going to be going over what we're trying to do in this iterative process. Okay, and yeah, let's first convert it to a PyTorch tensor. Okay, so we are going to be converting a Python list to a tensor. Okay, PyTorch tensor. So we have the Celsius first. Okay, that's going to be our output. And that's going to be torch.tensor, and we pass in TC. So we're redefining TC as like a tensor. Okay, so we're using the original definition of TC to redefine it as a PyTorch tensor. So that's what we're doing here. And let's do the same thing with TU. And the U here just stands for unknown units. Okay, and the C is for Celsius, if that wasn't clear. Okay, so we do that, and we're just converting it to a tensor because that's how we deal with our data, right? We can't deal with Python lists. And I think I made a video on why Python objects aren't that great in general, and it's because of the fact that literally every single thing is an object in Python, and every single thing needs memory, and an index to access that, and we just don't need that all the time. So yeah, that's why Python stuff aren't that great. So we're going to be using tensors. Okay, and that's the common way to deal with this sort of although this isn't that massive, right? It's just a regular list, but when we have real data, you can really see the difference. So okay, so we stuck with the conclusion that, or the assumption that this is going to be linear. We don't have any other option because first of all, it's pretty reasonable, I guess, to assume that. Once again, let me repeat that you cannot do this with real world data because you have no idea how the relationship's going to be in the first place. But like Kepler, we can just pretend that it might be something and just roll with it and train it based on that. And also we know that it's linear because I kind of made this data up and it's not real. So okay, and let's pretend that linear models was the first try. Okay, so let's pretend that a linear model was the first try. And remember what model means, right? Models just represent your data. They represent your data as a function. Just like we have the line, x plus 2. Just like we have the line, x plus 2, we model that with a line with the equation x plus 2. So like it comes in pairs, right? The equation comes in pair with the graph. So the graph is how we model that data, and we came up with an equation that represents some other data. So if we pass in the input from our original data set and we want to get an output, the thing that we're predicting, it's going to be f of x. Okay, and the thing I deleted just now, I'm going to go over it again in this video. I don't think we actually went over that in our last video, but it's like fine-tuning our parameters and whatnot, which we'll get into. Okay, so yeah, so if we're going to pretend that this is a linear model and that the relationship between TU and TC is a linear one, what implications does that make? Like, what does that imply? Well, a linear model or a linear representation of data comes in this format. We have an output that we want to predict. We have an input, which is multiplied by a value, which we call the slope, because that's how steep our line is, and we add a y-intercept, okay? And so, we have our TC as the output. Okay, TC as the output. M is our slope. Okay, M is just M. X is TU. And B is, it's just B. Okay? And we actually have special names for M and B in machine learning. And we would call them parameters. Okay? We would call them parameters. And so M, this is applicable only to linear units. Okay, the linear part. First of all, we only have one part in the example that we're doing, but actually, linear models, linear layers, linear sections of our neural network play an incredibly important role in the overall machine learning process. And you cannot go, most of the time without, especially if it's supervised learning, right? It's very common to see a linear layer, something that's linearly related, okay? So this is what we mean by linearly related. And also, when you start reading what other people are doing, maybe with their research, you might come across some linear algebra terms, and they might say, hey, this is like a linear combination of, some features, right? So that's just another way, of representing linear equations. So you're going to have multiple equations, and things are going to get more complicated, but let's just stick with the one simple y equals mx plus b. Hopefully you're familiar with that. If you're not, I would recommend reading more about it. It's quite simple, and we can actually go through the process now if we wanted to. So the best fit line. Okay, before that, let's give a name for our M. Our M is actually a W in, machine learning, and B is B. So W is the weight, and B you would call the bias. And the weight it tells you how much a given input influences the output, and you can see that, right? If W is really big, then this is going to impact, that's going to impact our output, our overall output a lot, right? Because we're going to be multiplying TU by a really large number. So that means we're giving a lot of importance to this specific input. And this will make more sense when we talk about different, classification models and other things like that. But, just know that it's something that we can play around with, just like our bias. And just like in a line, right? Like if your b is 0, then you cross the origin, and so the bias is what the output would be if all the inputs were 0. So it basically tells you how much bias you're making, right? So if you weren't really considering inputs, right? If we didn't even look at the relationship between the input and the output, what would our bias be, and if it's really big, then we're making a lot of assumptions here, and if it's small, then we're not. Okay, and so when you click on best fit line, right, when you see an image, this is really fuzzy. Okay, we talked about this. This line, or maybe we should get maybe not that fuzzy, but like this, or like this. This is really fuzzy. And this, like we talked about last time, is the trend line. Okay, this models and approximates our data. So for example, if we wanted to pick something that was at maybe -1, then we would predict that it would be somewhere around here. If you can see where my cursor is, it would be somewhere around 5, right? If you extended that line, and if the predictions and if the approximations were accurate, it would extend. And so basically this is fitting a line. This is training a model. And when we train our model, what we're doing is we're finding the perfect line that models our data. Okay, so in deep learning, we're going to have a lot more parameters, but in here, with our linear model, okay, so with a linear model, mathematical model that represents our data, we have 2 parameters. One parameter is the weight / slope. The second parameter, this is the first one, the second one is our weight. Is our bias. Okay, so this is our y-intercept. Okay. Imagine if we had some data, right? We have some input, okay, and we have some values, okay? So I'm just making them up. Don't worry, I'm just sliding my finger across the keyboard. Okay, so we have some input and we have some output. Actually, this is definitely not linear. So maybe 1 is 1, 2, 3, 4, 5, 6. Okay, that's the input. And the output is okay, wait, let me make this a markdown cell. And the output was 2. 1 second. 2, 4, 7. Maybe this is too close. Okay, wait, maybe 3, 6, 10, 12, 16, and 18. Okay, so this is a line. This is a fuzzy line because this isn't exactly times 3. 3 times 3 is not 10. 5 times 3 is not 16, but it is close, right, to 9 and 15. Okay, so we have a line. We have another line, though. And this line, we have another set of data, right? And this data is 5, 10, 22, 5, 5, 10, oh, excuse me, maybe like 16, 22, 25, and 31, okay? So this we could say is like y is equal to, 3x, right? And actually, if we were to have a bias, then I should have added maybe like 20. So 25 and like 30. Maybe let's say plus 20. And that's our bias. Okay, so we have y is equal to 5x plus 20. Okay, so we have inputs, we have outputs, we have inputs, and we have outputs. Okay, they're both linearly related, but they have different parameters. Okay, these are completely different lines. Okay, this is y is equal to 3x. This is y is equal to 5x plus a bias. Okay, the model doesn't know this relationship at the start. Your network, your machine, your computer does not know this relationship at the beginning. It tries to figure out the relationship as the iteration process goes on. So that's what the iterative process is, to get the perfect weights, the perfect biases that best models that data. So for example, if this was y is equal to like negative 2x or something, actually this is y is equal to negative x, right? Right, those are the perfect parameters. -1 for the weight and maybe 4.5 for the bias. Those are the perfect parameters you can get for this data. Okay, and the machine doesn't know that at the beginning. And so maybe at the beginning it just makes an assumption, right? We need to make an assumption at the beginning, okay? And then when we keep figuring out what the data really looks like and how we can model it, then our machine gets better. But first we need some initial set, okay? We need an initial set of parameters that will model the data. Okay, that will at least try to model the data. And the model, we definitely know that this is going to be wrong. Okay, that's the whole point of training. The point of training, okay, this is important here. The point of training is to identify the best parameters that will, let's identify the parameters that will best represent / model the data that we have. Okay? That's what's going on in the iterative process. That's what the training is all about. If your model gets familiar enough with your data, it's going to be able to identify the parameters that are going to model it. And that's what I was talking about at the beginning. I said I deleted something and I was going to talk about it again. And that was for example, if the actual data was, if the actual data was g of x is equal to 4x plus 9, okay? And our model thought that it was like f of x, right? So we're going to go along with f of x, and that's our end result. And we say, hey, I'm predicting some new, I'm predicting on some new data, and I'm testing this out, and we are passing in a new data sample, which is 4, into our model, even though it's completely wrong, and we get an output of 6. Our accuracy goes down tremendously. Okay, what is g of x plus 4? G of 4. What is g of 4? Well, it's 16 plus 9, which, it's 25. Right? So, we're wrong. We're wrong by a lot. And the model knows that. Okay, that's what I mean by the model getting familiar with the data. How does the model know that it's wrong? How does the model know that, hey, x plus 2, even though that was our initial assumption and we're expecting it to be wrong, now we know how wrong it is. Okay? X plus 2 is very wrong. And the thing that, let me copy paste this at the bottom so we have that for reference. So yeah, how do we know that we're wrong? We have a loss function to tell us that. We have a loss function. This is an important part of deep learning. We're going to be talking about literally all the components of deep learning, except in the next series, next couple of videos, except for the things that actually make it complicated. So I guess you could say well, then what are you going to be talking about? But the general process that Kepler used, this is the machine learning process. We have some data, we try a model, okay, that we think is going to work, might not work, right? We try to find the best fit line. We try to find that trend line so the model that you choose is going to define your parameters, right? So if we have a line, we say that our thing is a linear model, well, we know what our parameters are going to be then. We know that it's going to be a weight and a bias. I'm not saying that we know the values of them, but we know what parameters that we're trying to predict, right? So we take that data, we break it up, and we're focusing on the training part, fitting that data, really modeling it so that when we pass in a new data sample, we're not completely off like we are here. Okay, so that's the point. And so for every iteration, every time that the model tries to come up with a new model that, hey, I think I've learned from the past, let's talk about the first time. So then let's talk about the first time the iteration happens. So the first time we have some default weights and biases. Okay, we're completely wrong. And then we get 6. And then our loss function based on the 25 and the 6 tells us that how far we are. And based on that, we try to minimize the loss. Okay? To get the perfect parameters that make our function the best at modeling / representing our data, we need to minimize the loss. And we'll talk about how we do that in our next video, but you might need to brush up on your calculus skills, or if you aren't familiar with it, we'll go through the basics. Don't worry about it. But yeah, I might need to make some calculus videos for machine learning, and just to explain what that means. Okay, so we need to minimize the loss function. We want to make our loss the smallest it can possibly be. So if we have a parabola, right, that's upward, okay, you know what a parabola looks like, right? And we have that minimum point. It's not concave down, it's concave up. So we have a minimum point. We need to try to find that minimum point and try to optimize it and find the smallest value that it can be, because once we found the smallest loss value, once we found the parameters that minimize the loss, we found the parameters that best represent our data, at least based on the model that we're using, which is a linear model. Okay? So, yeah. So, let's talk about the loss function. Okay, not in super detail, but like, the loss function. So you might be 2 units above and you might be 2 units below, okay? So your data right here, you see how like the distance between the actual trend line and the actual value, right? That might be like a unit apart, right? But what we need to take into consideration is the fact that if our data is 2 units above, or if it's 2 units below, it doesn't matter, right? We should like penalize it the same. So for example, if actually not the data, never mind. Like if our predicted values are 2 units above or 2 units below, we should penalize it the same. So if our predicted values are 3 units above or 3 units below, right? It doesn't matter, right? We're wrong, and like if we're wrong, we're wrong. It doesn't matter like in which direction we're wrong, okay? So 3 units above or 3 units below the actual value, okay, we should penalize it the same. So what does that mean? What does it mean when we like punish the mistakes that our model makes? Well, it's just like, any sort of punishment. Like if you do something wrong, I mean, depending on how bad the thing is, right? Like you punish it and you say, hey, this is not where you should go. This is like, this, like if you're way higher than the expected value or like the actual value, then, there's this formula that you can use to measure how far you're off, and you can define your loss function. Okay, so you can define your loss function, which is the function you want to minimize, as follows. So these are 2 simple ways you can do it. One is like taking the absolute value. I think it's the square of the absolute value. Or actually, no, it's the absolute value of the difference between the predicted value and the absolute value, right? That tells you how far you're off. Right, doesn't it? I mean, you can't get more, right? And the reason why we take the absolute value is because, it doesn't matter whether it's -3 or +3. When you take the absolute value, you should look at it the same way. So let me put that under the absolute value section. Okay. And the other thing you can do is take the square. Instead of the absolute value of the difference, you can take the square of the difference between the absolute value, between the predicted value and the actual value. Okay? And both losses have a minimum of 0, right? When you take a function of the absolute value, the minimum value the absolute value can be is 0, right? If you take absolute value of x minus y, where x is your predicted value and y is your actual value, or the other way around, right? The smallest it can be is 0. You want that difference to be 0, right? It should make more intuitive sense now that you want the loss to be 0. You want that difference between the predicted value and the actual value to be 0. So what does that mean? Well, it means that the predicted value is the actual value. Well, I mean, you shouldn't overdo this because this would result in overfitting, but, you know, like, you get the point, right? We want to model the data as close as we can and as best as we can. Okay, so, yeah, and we can take the square of the difference, okay, and we do this because if we want to punish extreme values a lot, like, this tells the model that, like, this loss is extremely high, modify the parameters, like, by a lot, okay? And, you know, check and see what happens. If it's too much, then we can go the other way. But we want to punish the values a lot. And the model is going to get that message that, like, I'm completely wrong, okay? The model is going to get the message that it was very wrong. Okay, so if you have even if you have, like, a larger, like, difference, even though that's not too crazy, the square of that difference is going to be crazy. So that's how your model is going to know. And although the minimum of both of these, the minimum of the square root function, the square, right, like, you can square 0, and you can take the absolute value of 0. The minimum is 0. So although the minimum is 0, there are some things that you want to keep in the back of your mind, and that is the derivative at the points, okay, at that minimum. So if you take a look at the absolute value function, you know, it's a v, right? It looks like a v. Maybe we should search, like, absolute value function graph. You know, there it's like it's a corner, right? That corner means that, like, the derivative is 0, right? We can't, the left side limit and the right side limit are different, and so we don't have, our derivative is undefined at that point. Whereas if you take a look at the the square, like, x squared, right, function, we get a nice parabola. It's a nice smooth curve, and the curve is, like, you know, it has a derivative of 0 at the minimum. Okay, so it has, like, a horizontal tangent at the bottom. So this is going to play an important role because we are going to be using derivatives to and, like, gradients to, like, minimize that loss and to optimize our performance and our function. So derivatives are going to play an important role in figuring out, like, what the best parameters are. And so derivatives, okay, so, right, we might want to, there are definitely ways we can get around this, but so just keep that in mind, right? Okay, and these are both pretty simple, and there are tons of more powerful loss functions out there, But, these are good for learning purposes and just to figure out that, just to understand that, like, hey, the loss function tells you how wrong you are, how far off your model's, your model's prediction, of f of x, how far this entire model is wrong, the parameters are wrong, and, like, these loss functions let the model know. Okay, the difference, like the model knows the difference between the predicted value and actual value based on the loss function. And so based on the loss function, we'll tweak the parameters, okay, to make it the perfect line that we want. And we're going to be going through the implementation in another video. So yeah, we'll just define the model, we'll define our loss function, and we'll initialize our parameters, right? Because we have to initialize it with something. We know that we're not going to be the best at the beginning, and we might pick a line that, goes through the origin, when in reality, if you model the data perfectly, it might have a y-intercept at 4 or something. So we need to pick some initial values that are going to be wrong that we can fix later in our training. Okay, so that's the plan for next time. And I think we kind of reiterated multiple times the main points of today's video. So I'm not going to be going through that again, right? We have actual data and what our model thought it was. We talked about loss functions. We defined the problem statement that we're going to be working on. We talked about how linear relationships play an important role in real complicated deep learning models, even though nonlinearity makes it interesting. And we converted it to a tensor, although that wasn't the main part. Okay, we talked about their different parameters and what they mean, and weights and biases, and picking the perfect parameters and what that means. And we talked about loss functions and examples of pretty simple loss functions that are great for learning purposes, and just to keep derivatives at the back of our head, the back of our mind, so that we can talk about them when we are optimizing our model. Okay, thank you so much. I know that was a lot, but hopefully you got something out of it. Hopefully you learned something, and I'm looking forward to seeing you guys in my next video. And don't forget to like, comment, and subscribe. Thank you so much.